today and the technical problems, and also for not having the proper microphone. But anyway, so we're very happy today to receive Dorlis from the National Technical University of Athens. And Panos will talk to us about how much can gravitons be squeezed. So please, you have the floor. If you have questions, feel free. There will be time at the end, and also, don't worry, you can extend a bit at the end so that you have still time to present. So thanks again for being here.
Okay, thank you, Jordan. But most importantly, thank you for giving me the opportunity to give my first time in a very friendly environment. I'm really happy. I will present today a work of mine with my supervisor, Panagiotis, together with my colleagues Dorlis and Professor Saber from the King's College of London. You can find our article here, the later version, but we have also this long companion, but it's under construction and we publish it probably to ERD. And actually, all of the talk today will be we try to introduce it to a cross-fertilization between from transport. Okay. Yeah. Okay, let's continue. Okay, I will try to introduce to this cross-fertilization of ideas between quantum optics and the quantization of gravitational waves in order to explore some quantum features that we can find to be detected gravitational waves by interferon. That line of the talk, I will start with an introduction in which I will start with some arguments. Yes?
The slides do not change, I think.
Yeah.
I am in the front slide.
I am the second one.
Yeah,
Okay, I see the first one.
Yeah. It's here. Do you mind if we do the entire screen? Yeah, but the presentation mode is messing up.
Okay. Here and here.
Okay.
Now you see the second slide? Okay. So I will start with an introduction and okay. I will introduce some arguments by Dyson in order to detect the quantum nature in the gravitational waves, but actually his opposition that we cannot do it. Then I will proceed to the quantization of gravitational waves, actually involving an EFT approach for the general relativity. And then I will define what we mean with collective gravity states. I put graviton in parentheses because actually it's where the quantized fit these definitions. And then I will show a class of collective graviton states that are purely quantum in order, but they admit a large occupation number of gravity. And they are the best papers in order to detect some quantum nature in the gravitational waves. These states are the squeezed states. And then I will show how in quantum optics people work out distribution using lasers and crystals. And then finally I will go to our article in order to bring the ideas to the gravitational atom produced through the superadic stability. Then I will conclude with some comments on how one can constrain the action physics to know the results of quantum gravity. So, we are only indicating to the gravitational wave strong. Using interferometers, we can measure distances with high accuracy and then detect the gravitational waves So far, we have only detected gravitational waves from binary, and we are only limited to the final process of the merging, which are gravitational waves with increasing frequency, that is not constant, and increasing amplitude. Here I have some acoustic transfer of this signal that doesn't work, that's okay. In which you see the signal get higher frequency and down. But this is very good because we have a new way of fundamental physics, gravitational waves. And actually, I mentioned here a new article in the literature in which this collaboration tried to prove the area theorem of Hawking, which is very good because it also verifies some conditions like the null energy conditions, the area theorem, and this is what we want to do to prove fundamental physics with gravitational wave. These are the sources of the gravitational waves. We have only taken these, but there are also some sources that are continuous, which are characterized by the level duration of the signal and the constant frequency that they have. One such source is the superradiance and the reaction cloud formed around the black holes. In brief, the superradiance stability consists of instability between the interaction of a boson field outside the rotating black hole, in which the boson field extracts energy, actually rotational energy, from the black hole and forms a condensate-like distribution around it with a large occupation number. Now, it is very important that this atom emits gravitational waves in such a low rate that it has a very long lifetime, and this lifetime, which depletes, actually it's because it depletes through gravitational waves, this time scale is much larger than this instability for the cloud to be formed. This severs the apparatus in order to this cloud actually go to saturation and then have a stationary stable configuration of a large occupation number with a very, very long life. Indeed, this is the case. As you can see here, some values in the parameter space. Here is the Hubble time, the edge of the universe. You can see that there are some parameter space in here that we can exceed this time, which means that this gravitational atom is actually stable. Here, this is the plot of the derivative of the frequency, where it's indeed so small. So we have a constantly monochromatic gravitational wave we get. So, Dyson raised this question: can we detect a gravity, a single gravity, raised just 2 years before the first detection of the gravitational waves? And he raised the fundamental question of the quantization of the gravity. If we can detect a single gravity, this will be a direct evidence for the quantization of the gravitational field. But this can't be happen. The reason of Dyson was to compute the energy density of the gravitational waves, and specifically for a single strain and frequency, and compare with the single quantum gravity regime, which has this scaling to the frequency, the density, and then if we divide these two frequencies, we see that we get a very, very large number, which means that the detected gravitational waves from the LIGO contain a macroscopic number of gravities. So, since we have detected the gravitational waves, according to Dyson, this is not a proof for the quantization of the gravitational field. What if we want to detect a single gravity? Take this ratio to be just 1 and see what is the strain in this dielectric regime and which is the response of the interferometer. The measurement accuracy is given by this, and if we have an optimal sensitivity, which means that we have the wavelength to be comparable with the outlet, then we see that in order to detect a single gravity, we have to acquire a Planck length accuracy for our measurements. But this means by simple arguments that if we apply the uncertainty principle to the one mirror of the interferometer at the time t and imply causality for the measurement, which means that this is going to be larger, the variation actually collapses into black hole. So this means, according to Dyson, that actually nature prevents us to detect a single graviton and actually the quantization of the gravitational field. But this main assumption is that we have to detect a single gravity in order to detect the gravity. But from quantum optics, we know that there are states that are purely quantum in origin, but contain a large occupation number of excited states. So, in order to study this, we have to set quantum to set the framework. Actually, the framework is to see the general relativity as an effective field. Okay, the problem for the quantization of the gravitational fields is that this theory is not normalized. And actually, this implies that it's not a predictable theory. But this is true only in the large regime, in the large energy regime, which is the UV interval. Yes. But given the general theory as an effective theory, actually we can make predictions to the low energies, which is actually the regime of the detected gravitational waves. So this is very good to enforce such an EFT approach and study the quantum waves for gravitational waves. Starting with the Lagrangian of general relativity coupled to a scalar field, minimally coupled with it. The particular approach consists of taking a fixed space-time background and introduce a metric perturbation, and then treat this perturbation as a quantum field. We expand up to second order, taking these large Lagrangians here, but this contains unphysical indication field. What we are going to do is to quantize the theory with canonical quantization, which means that we have to disregard the unphysical degrees of freedom that they are contained because of the gauge symmetry of the perturbative approach, which actually follows the general covariance of the complete theory. Then fixing the gauge to the triple gauge transients transverse, imposing these conditions to the metric perturbation, actually our Lagrangian are too much simplified. This is the free graviton because it does not contain interactions, but we see that the background curvature sources the graviton to the second order interaction. And here we have the material Lagrangian in which we have two terms. We have a linear term, which is actually the term that produces the gravitational waves, and we have also a second order interaction to the graviton, which I will see will be responsible for the squeeze states to be produced. So, under certain circumstances, we can approximate the background metric with a flat approximation. Then the Lagrangians are simplified more, taking these values, in which we have also only the special components because of the vertical transversal gauge. And then we take all the three Lagrangian in order to define its quantization. We proceed to a Fourier expansion of this metric perturbation, in which here we have the polarization vectors, and we use the helicity basis, which is actually a linear superposition of plus and cross polarization. We use half. And then, plugging this into this Lagrangian, actually, we arrive in a simplified result, which is that the two polarizations actually behave like two independent scalars in the Minkowski background, which we are very familiar with this, and we know how to quantize by defining appropriate creation and annihilation operators of this form. Here I have quantized just in a box volume 3 in order to make everything here dimensionless and bring the dimensions of the perturbation onto here. Then we are in the Minkowski background, and we don't have problems in defining the vacuum, which is uniquely defined by the action of the annihilation operators for all the polarization and momentum. And then we have also the creation operator. In which we define the excited state with powers of the creation and annihilation, the creation operator, and linear combinations of them. Having this, we can define the collective states. And what follows in this section, I will not
Since you're really on the curve background rather than Gaussian, do you, I guess you're assuming that this is taking place far away from the horizon, but do you have any idea how will that change? I mean, people know about phases, functions on curve. That will be much more complicated, but
too much complicated.
Yeah.
It's also complicated, but also in principle, because you have a not neatly defined fact. You have somehow to transform to find the true vacuum, your defined property in the curve account, and then transform it to the Minkowski that we are and we measure. This is very complicated. So in here, we just first approximate it in the Minkowski in order to see qualitative behavior.
Mm-hmm. But do you have any estimate how far you would need to be from the horizon for this to be good approximation? Because I guess that might depend also on the size of the black hole. Because the curvature.
Actually, as we will see later on the Athens, we are in the non-relativistic limit, which is actually we are far away in terms of how they partly. Actually, this is the first approximation to the status to the super Athens. Everybody takes the flat approximation in order to see the qualitative behavior, and then you have to proceed further in order to have also. Okay, so this is some basic literature from quantum optics that I've used for this next slides, and especially this one of Agarwal and Greenberg as we have them. And I will start with the coherent states, because the coherent states are the most classical states. They are defined as the eigenstates of the annihilation operator, and they are completely defined, determined actually by this coherent parameter, which in general can be a complex number. As usual, in order to collect all these things of our creation operators, we define operators that act on the vacuum, and this is a collective state because we have an exponential here, and you have a series of excited states in which you want to find the mean value of the particles, the variances, and etc. For the coherent states, the transformation of the creation and annihilation operator is just this. It just shifts and displays the annihilation operations, and consequently also for the creation, which you just take the dimension constant. Now, using this, you can find that the variance of the number of particles in state admits Poissonian statistics, and this is a characteristic of the coherent states. Any departure from this Poissonian statistic means that it's a degree of coherence. As you can see here, with the larger values for the coherent parameter and the larger number of the excited state of the quanta in the state, it gets larger, allowing a deviation from the mean value. Now, another feature which is very common in quantum optics communities is the phase-space representation, and the quadratures defined like that, so the annihilation operator. It is actually you can think there are one oscillator, which is the position in momentum, the conjugate value that constitutes the relation. Then In this phase space consisted of the momentum and position, there are definitions of quasi-probability densities. And I say quasi-probability because they are not actually probability distributions. People do this in order to be close with a classical description of probabilistic theory in order to describe the states. And this is the Wiggins function on this phase-space presentation. Now you see here for the vacuum, which is just the coherent parameter, it will be 0, that this probability centers at the center the zero momentum position, which actually you can see the harmonic oscillator lies on the center here, but you have some uncertainty around it. It's like a Gaussian-like distribution. Actually, it is a Gaussian distribution around the center. And for the coherent states, this structure remains the same. But due to the coherence, this is moved to another region rather than the vacuum. If you take the harmonic oscillator, for example, to oscillate around the center, you will see here, classically, we have a trajectory well defined to be here. In this case, you will see this, like to move the classical trajectory, but to carry on the uncertainty. And the uncertainty here, the coherent states, are minimum uncertainty states, like the vacuum state, that saturate the uncertainty principle in a way that we have both of them to be 1 over the square of 2. Another states are the squeeze states, but we define it through this squeezing operator, which is quadratic to the creation and annihilation operators. This is the squeezing parameter, it can be complex. This is the magnitude in the phase. It is also unitary. And here, the crucial point is that the transformation of the creation and annihilation operators takes this form. This form is like a Bogoliubov situation that connects to a vacuum. Coming back to your previous indicator, actually this transformation connects differently defined vacua in the curved space-time. For example, in the cosmological background, if you want to connect the vacuum at inflation and vacuum under radiation, these are connected through this transformation, the Bogoliubov one. And this is why the inflation also produces squeezing the cosmological state. Importantly, though, we see that the mean number of quanta in the state is given completely determined from the magnitude of the squeezing parameter with this way, and we have also that the variance is super Poisson, which is the first imprint of a coherence. But more interestingly, we see an exponential dependence on the squeezing parameter, which means that for at the order of 10 for the squeezing amplitude, we get a large number of excitations in the which is also true for their coherence. Now, the three-space excitation, the Wiggins function, takes this form, and this is why we call this state squeeze, because it's like the Wiggins function of the vacuum or the coherent state, but it squeezes in one direction, but with an excess noise to the other direction. These are also minimum uncertainty states, but in another way. In the case that we have the vacuum, we set this 0 or just coherent, and we have just both of them together. In here, we see that in the one quadrature, we can acquire some vacuum uncertainty and go beyond, which some usually actually also in gravitational wave detection. This can be used in order to increase our measurements of uncertainty and be more accurate in order to measure quadrature. Now we can have the squeeze coherence. which define by the action of both the operators. They do not commute these operators, but there is a determined relation between the commutation. And here we have that actually we have a displaced from vacuum like the coherent state, and the transformation here takes this form, which is a Bokoliubov transformation, but displaced due to the coherence. The total number of gravitons or quantum in here is just the sum, and we can define this Mandel parameter in order to quantify the coherence due to the non-Poissonian statistics. Very interesting in here, we see that in some parameter space, not only super Poissonian statistics emerge, but also sub-Poisson, which means that we can have a narrower uncertainty around the mean values for the graviton states. These are very crucial properties, also the squeezing and the sub-Poissonian statistics, because actually it serves a way in order to define the non-classicality of the states. In order to do this, we use the P representation, which takes advantage of the fact that the coherent states satisfy completeness relation, which means that it is a basis, but it's in a non-orthogonal states between them, except for large deviations of the coherent parameters. And this means that we can express every state into a sum of coherent states. And define here, again, another phase space, which is constructed by the real part and the imaginary part of the coherent parameter, and define, again, a quasi-probability distribution. Now, if this quasi-probability distribution have the properties of a classical distribution, which means that it's strictly positive, smaller than 1, and it's totally smooth, then actually every state that we have, the quantum state, can be mimicked by classical theory, and we can of the probability. And this means that we cannot distinguish between. But these properties here, the squeeziness and the sub-Poissonian statistics, signify a non-positive definite field function, which is also highly non-singular. And this is actually the definition of the non-classical states, because these effects cannot be made at all through a classical theory. So what we have these squeezed states to acquire purely quantum properties, and you can have a large occupation now. So these are the states that we are searching for in order to bypass the Dyson opposition in order to get the quantum nature into the gravitational waves. This was realized in 2021 by Barry Wilson and Zachariadis. And this later form of the article, but also the long companion, which is a very good article, but too lengthy, and I will not present everything because it's quite manual. But I will present the main results of this. Here we have the interaction in a Fermi and normal coordinates in order to be variant, and expand the action of the separation here of the two free particles of the geodesics, and find the linear interaction between passing gravitational wave in this direction and the separation function of the two mirrors of the interferometer that these apparatus can meet. So, if we treat the theory of the graviton in a classical manner, we just take this equation, which actually is responsible for this wave behavior between the two mirrors or the two free column particles, which go when passing the gravitational wave like that, when we are to the plus polarization. But this drastically changes if we acquire a quantum theory for graphs or basic perturbation. Actually, they enforce the final version of the Vernon formalism, which is like to find a response to the system which is dissipated by linear interaction, and actually we find the effective Lagrangian and the effective theory. And then we can find the most classical part of this effective theory. It actually arrives to this very interesting result, that the geodesic equation becomes a stochastic, like Langevin equations, because we have here this function which is stochastic and Gaussian and determined by this Gaussian distribution. Now, what does this mean? Because of this structure of the Gaussian distribution, this function is a random stochastic function and it has zero mean, which means that it's a noise. So, but it has a non-zero correlation function. And most importantly, this correlation function is state dependent on the gravitational field. We take another for the vacuum, another for the squeeze. Here, this result is it takes the coherent state, which admits the classical gravitational wave, and here the noise arises due to the vacuum or the squeeze. Solving approximately this equation, we take this form, and we see that the mean value is like the classical equation, but it has a non-zero values, which is state dependent and determined by this stochastic function here. What is this mean? The noise and the deviation to the classical equation that the vacuum imposes, it is again to the Planck scale. So, with the argument of Dyson, we are completely out of goal in order to detect some deviation. But if we have the squeezing in here, we see that this exponential behavior that the squeezing admits transfers into the deviation to the classical geodesics of the mirrors. So we can have an enhanced deviation that potentially might be detectable if we have a large enough squeezing parameter. This is very crucial because an exponential enhancement can be acquired only if we have a squeezing parameter larger than 1. If we have smaller than 1 squeezing parameter, there's no exponential enhancement and it's like a vacuum and no detection at all. So all the story here is to find astrophysical sources that might produce such a squeezing which is larger than 1. This is a main problem because the squeezing will be an effect of the EFT theory, where all the effects are suppressed by the energy scale that we have to our radius through the Planck scale, which is a very small quantity. And actually, this is the reason that we can acquire the effective theory. But on the other hand, this is the reason that all the effects are negligible. So, but we can have some operations in order to potentially enhance this thing. Before that, I will introduce how we can produce squeezing with layers and crystals in quantum optics using the quantization of the electromagnetic field, and then go to make the parallels to the gravitational atom and identify what the ingredients in this case will be. Okay, in quantum optics, when we have a medium, the electric field, I assume magnetic field to be 0, polarizes the material, and this back reacts to the electric field. So the Maxwell equations are formed through the displaced vector, which actually, and its energy is given by that. When expand, we have an interaction term and self-interaction term for the electric field. There are materials that are linear dielectric. That should mean that the polarization will be just proportional to the electric field. This just shifts the basic energy of the electric field. But there are materials that are non-linear, which means that the polarization will be to the second order of the electric field, which means that it reduces an interaction which is third order to the electric field. But As we saw previously, in order to produce squeezing, we have to take second order to the operators here. But we have a third order interaction. So this is where the laser comes, because we send a laser into the crystal which induces the nonlinear interaction of the electric field, and this replaces the one operator which doesn't see now. And actually this is the source of squeezing. This will determine how much squeezing we will take together with the characteristics of the nonlinear interaction. So if we take a laser, send it into a crystal, we have a coherent field, which is like classical, interact non-linear. And this actually produces a Hamiltonian which takes this form, sorry, in which we have keep only the energy conserving terms. The other terms are denoted by these dots, and through the rotation wave approximation, we eliminate them because they are highly oscillating terms and they not contribute so much like these classical ones. It's like the path integral formulation when the stationary phase, it's the most common class. Here I note just simply this notation, the vector k and the polarization of the electric field. And because since we have this Hamiltonian, the evolution operator takes this form, which is exactly the form of a squeeze state. But with a crucial difference in here. This is not a single mode squeeze state. It contains multiple modes of the electric field. In order to be reduced to the single one, the single mode, this has to be a delta function in this. And then apply only one mode in order to be squeezed. There's also another way to use squeezing, which is if you have a material which is highly nonlinear, and actually with polarization that has a third order with the electric field. In such case, we have four operators here, which means that we have to set two coherent states, and then two photons interact and produce in this coherent state and produce two entangled photons in here. And with this setup, we end up again with such Hamiltonian, but with more energy available for the immediate photons. And also, very crucially, that we see in the next slide, that we have two coherent speeds and we have a square of the amplitude, which requires more and more enhancement of the squeezing parameter, which depends on these coherent fields. So what we need in order to produce squeezing? We need nonlinear interactions and coherent fields that are most classical fields. In general relativity, it's highly nonlinear. We have this. We don't need any crystal or something like that. We have a nonlinear interaction to be up. But what we need is a coherent field. The role of the coherent fields will take place from the action cloud around the black hole. So we will see that in here, such processes beyond the classical gravitational waves that will be emitted. There will also be processes like that that will squeeze this gravitational wave. And here comes our argument. We start with the gravitational transcript theory because mostly in the literature, the other super-radiant boson, which we take here to be a pseudoscalar field, it's treated like the action. So we introduce also the Chern-Simons interaction, gravitational Chern-Simons, which is like the magnetic interaction Chern-Simon, which is defined by this, which is product of the Riemann tensor and its duals. We can be formed also with the flat LLC beta symbol. Varying this action with respect to the method in the action, things were required and modified equilibrium motion, which are defined through this quantum tensor, which has the important property that it's not divergent. And this actually puts in question the general values of the theory, but it's not the case as usual in the modified theories, since it is the generalized energy momentum tensor that is concerned, and thus we have a general covariant theory like the NGR. Now, these couplings actually arise as effective couplings, which means that here the couplings are like the Wilson parameters of the effective theories, which means that they are very suppressed from the UV cutoff that we have in our theory, which actually we take it to be to the order Planck or the string scaling if this theory arises from the strings, which actually does. Now, in the Z-Simons theory, we know that Kerr solution exists. So the Kerr solutions are modified. But due to this effective coupling, the effects in the black hole can be quantified by this parameter, which is here is the GM, which is the order of the curvature, and actually the horizon, which is the scale of the black hole. And here are the scales of the black and the scale of the couple. So if you take this to be just proportional to the Planck length, we have that these effects are very separate. So we have deviations, but we have very, very small deviations. So on first order, we can take it just to be like we can. And moreover, studies for the black hole superabundance in the Z-Simon theory show that actually the superabundance behaves much like NGR, at least for the nominal mode, which is the 2p state. So, in what follows, we take just the black hole superabundance as described in original German idea, which means that we have the Kerr black hole and the standard notation here, and what we want actually to see is this equation of motion for the boson field to an upper cube Kerr background, and we don't consider the back reaction of this field, which is like effect. So this equation takes this form and can be separated in variables by taking this answer. Here is the angular part, and this is the radial part. With the separation constant here, with the angle values of the separator. Now this is quite difficult to show, but in the non-relativistic limit, which physically means that the component wave of the field is larger than the dimensions of the black hole, this actually simplifies. And the solutions, it is known that take the heterogenic form, like the heterogeneity. And this is why in the literature it's called the gravitational act. Where here, this parameter that quantifies actually how strong is the interaction between them, it's like the fine structure in electromagnetism, but the gravitational one. Now, we have all these modes, the NLMs, like the hydrogen atom. These modes, they are not all, every mode is super. Bekenstein here, he didn't consider this to solve actually the equations, but only used the black hole mechanics and the area theorem and the validation of the numerous condition in the horizon in order to prove that modes with the real part of the frequency which corresponds to the energy, if satisfy this condition, which here have the angular momentum velocity of the horizon, then the energy is extracted from the horizon and the black hole. In view of this formally, it turns out that this is a complex. The frequency actually here is complex. And if this superabundance condition is satisfied for some modes, then this imaginary part gets positive, which means that we have growing modes. And the cloud takes energy. The most effective one is the 2p state of the hydrogen atom. And this is why, because the superabundance scale here, which is the time scale in order to start with a small perturbation and have the full saturation of the cloud is the smaller one for the Turpi state. And also, this admits that it leads to a very extremely large occupation number for the actions in the cloud. You can see here the orders. This is a very, very big number. Moreover, the cloud is concentrated far beyond the horizon. We can quantify this by taking just this expectation value as we do in usual quantum mechanics in order to find the Bohr radius. And actually what we find is that takes the usual thing, but in here we have the gravitational Bohr radius, which is given by this term, which is inverse to the non-relativistic parameter, and this is why the cloud, its main contribution, is formed very far from the horizon. And this is why we can form the flat space approximation at first hand. So in brief, we have the gravitational lag, the stability occurs, the action cloud here goes to saturate, it doesn't anymore gradient, and stay at equilibrium. We have the quasi-gravitational integration that emits gravitational waves, but emits gravitational waves with an extremely large lifetime. And this is why we have a continuously and constant frequency gravitational wave signal to occur. These characteristics here, these are the crucial ones of these operators in order to enhance this one gravity of the effective theory phenomena. These are the action-gravity interactions with the flat space number. Here we have the general relativity interactions, in which we have the linear term, which corresponds to the evolution operator with an exponent linear to the creation and annihilation operator. So this is responsible for the coherent states of the gravitons, which are the classical gravitational wave. But we have also second-order interactions with the graviton due to general relativity and also due to the Jen-Simons coupling. Now, here, since we have a quadratic dependence on the action field, this process here that induced through the general relativity mimics the spontaneous wave mixture we saw previously for the quantum optics, which are two actions annihilate into a pair of gravitons. And the Jen-Simon one, which corresponds to the spontaneous parametric down conversion, which actually is a decay of the action to two gravitons. And these gravitons are entangled. So, as we saw previously, in general, we have a multi-mode squeeze state. A multi-mode squeeze state is defined through this operator, which mixes all of the modes of the field. And this can be seen through the transformation of creation and annihilation operator, which takes this non-trivial Bogolyubov transformation. This is also Bogolyubov transformation. We see that this mode, it mixes with every mode. Previously, we had that this creation, this annihilation, also has creation here, but on the same mode. And here, transformation mixes all of them. This is very important because it uses entanglement into the state, which is beyond the squeeze state of the single mode. Now, we can use this and find that the number of gravitons are given by this quantity, which is a series expansion of this parameter. And this means that we can set an upper limit on the number of the gravitons we have in these states. The single mode squeezing comes when we have such squeezing multi-mode parameter. And then this sum reduces to the usual amount, which is given by the sign of squeezing of the amplitude. Now, as we said previously, if we have smaller than 1 squeezing amplitude, then we don't have exponential enhancement. If we go in parallel, Then, if we have this step to be smaller than 1, then we do not have an exponential enhancement also in the multimodal case. Which means that we can see this step here as a mimic of the single mode squeezing parameter if we have here the Taylor expansion around 0.
Sorry,
Yes.
something that I maybe haven't quite gotten is this squeezing parameter. What does it represent? Or how does it relate to property of the system? Or
The property of the system.
is it something just from the theory? Is it something, say, that depends on the mass?
You mean in general, or in our case here, for the gravitational line? In general.
Let's say here.
Okay, the squeezing parameter is responsible for the squeezing effect of the state to the representation and the Poissonian statistics and all the quantum nature of the aspects inside the state. This is what I told you for the collective.
Yeah. My question is more,
Yes.
say, what determines its value? What determines if it's larger than 1 or not?
Okay. This is what. Actually, it's determined by the coupling of the nonlinear interaction and the source of the nonlinear interaction, which in our case will be the action, the action. So what we want in order to just start getting this exponential enhancement is this quantity starting to be larger than 1. If we apply this, then we have first the results in order to enhance this quantum gravity effect. Now, let's start with the CS induced, which is the action decay into two gravitons, and we use this PDC of quantum optics. And here we have this notation. And remember that here we have the integrals in the momentum and the sum of the polarizations. Then we look at specific solid angles in order to simplify this result, this expression. And this is just what determines the order. This facts here. And you see the suppressions of the effective theory. It's the scale of the action and the scale of our apparatus, they divide by the Planck scale. It's too small. So here we see the correlation of the two gravities. And we plot here, just for a specific case, this sum looking at the psi axis, and we have observed that the maximum contribution comes when the two gravitons share the same energy. It's divided just the mass of the action over 2. And we plot for this parameter to be just 0.1, which is the limit action in the literature of the non-relativistic approximation. Now, because we have this, we see that we have an almost anticollinear emission of the gravity. Because the actions inside the cloud are non-relativistic, and the gravitons are, so they are emitted almost anticollinear. If we increase in principle this, but we go out of our approximation here, this graph here will be enlarged, which will induce more squeezing, because this will mean that more modes will be entangled with each other. And more commonly, we see here that only pairs of right-left and left-right polarization are emitted through the Church angle interaction, which means that this is a best state in polarization. So we have a maximally entangled state in polarization for the graph, which is very hard in order to be observed even for particles. But this is highly extension, non-trivial extension of the single mode case, in which we see the also beyond the non-relativistic limit, we have more and more squeezing and entanglement. Now, quantify the result. We see that this ratio is very small. It's also to the fourth power. This is very, very small. But we have some enhancing parameters. This term, the capital one, actually is the lifetime of the action cloud, which is large. And also, we have the occupation number here of the actions in the club, which is also large. These are the enhancement parameters. But in the Z-cycles case, we see that because we have a linear dependence here to the number of the actions, this is not enough in order to compensate this operation. And we have also this term, and when we take these values for if we acquire the string effective coupling here, we find that this upper limit is very small. It has this enhanced parameter, but it has this ratio. So in this case, even if we have such a large enhancement due to the actual lifetime, which can be acquired in here and lead to this order of magnitude, this is so small that actually counts as no. It's like the vacuum. The only deviation is on the plankton. You will not see that.
So the capital T is the lifetime of the cloud due to classical depletion from
Yeah.
the emission.
Just actually, when you see, if you consider this as the evolution operator in the interaction picture, is the time of the interaction, on how much time this interaction takes place. And since this is a bound state, the action, this interaction takes place as much as the gravitational waves are emitted, and the action is as like that. Okay. Okay. So no, in this case, Tyson says no. Let's go to the GR case. In the GR case, we have a similar expression here, in which we see that the correlations here take this form. In such a case, we have the left-right and right-left polarization, but we have also left-left and right-right. This means that it is an entangling state in polarization, but it's not maximally entangling state. It's not a bad state, actually. It's approximately bad state because you see here, this subdominant to two orders of magnitude through this combination left-right and right-left, but it's not an approximately bad state. It's not entangling. It is entangling, but it's not maximally entangling. Also, we see here again the effect of the non-relativistic limit, which is that we have again almost anticollinear emission. And again, if we increase this parameter, but we cannot do it in our approximation, this would be enlarged and we diffuse more entanglement when we move into the relativistic limit. What is the order of magnitude? In here, we have a crucial dependence, which is that the number of particles comes to the square, which is not the case of the actual decay due to the Z cycle. This is due, it's like in quantum optics because we have two coherent fields that interact and give rise to the entangling photons. This dependence is very crucial because actually can compensate this very large impression from the division of the due to the Planck scale and our apparatus. Here we have this goes to a tractable number. It's just 10 to the -5. And if we go to the same logic as before, we see that this actually upper limit takes this form, which due to the scales of the action lifetime, it starts to get or indeed an exponential advancement regime, which means that due to the general relativity interactions, it might be probably possible to have this enhancement of the squeezing parameters and have probably detected in the detection regime such quantum gravity effects. But of course, this is just order of magnitude estimates. A more accurate analysis have to be done with numerics that you know here very much better than me. But I hope that I convinced you this is probably a nice case in order to search for the quantum gravity effects.
Can I ask a question? So, but this effect of the production of the squeezed gravitons is still very tiny as compared to the classical emissions. So in terms of the overall energy, that's going to be
The dominant one is skewed.
but I mean, what is the hierarchy of energies? Just to have a notion, when you are in this regime where you get this coupling here of the order of one, that could be interesting. Still, how much is the comparison of the depletion energy in terms of the classical regime versus this? So we want to understand what's the power emitted in this channel versus the power emitted in the usual classical channel. Well, still very tiny, I guess, very tiny.
I think it's smaller, yes. We don't have a very large squeezing parameter here. As we increase the squeezing parameter, then this will be confirmed. And actually, this is not a signal, it's a noise. You have the classical gravitational wave, and you have noise. So in order to detect these effects, you do not detect signals, you detect noise in the signal, which is very more challenging, I think.
But not any noise, some kind of specific type of
Yeah.
noise. That's the
Yes,
key,
it's
right?
not white.
Yes.
It's not white. It has correlations, it has characteristics. Actually, the characteristics are the Sampson statistics, are the squeezing that is produced in this state, it's transferred to the electric field in the cavity, which means the interferometer. You have all these characteristics, but it's also very challenging in order to detect, because this deviation, even if we have an enlarged effect here to the source, our detector, it's not so enhanced. So the effects are still suppressed. So you have to find ways in order to detect these effects, even if they are produced innately. The first thing is to find the sources. The next one is to find on how you can detect and identify actually this one. So just a comment here, and then conclude on the observational prospect. In this paper here, in 2023, Helmut and Lieder considered single mode squeeze states, but not a single mode. They take a Gaussian profile of single mode squeeze states, and they make left to interact with the interferometer. What they find is here that the deviation, the noise, will be like that. It is the correct scale, but has some differences to the parameters with respect to the other approach. Then they have the characteristic frequency that the Gaussian profile is big, and they calculate from this data, I'm not an expert from this, I'm just referring, and they find this deviation to the signal. So this means that we can put constraints on how much deviation and noise we see on the gravitational signals. We can put constraints on how much squeezing we see and having this thing. Just take this to be smaller than that. It cannot have a smaller squeezing parameter, because if it has a larger squeezing parameter, then the noise would be more large. So this puts constraint on this squeezing parameter. It says that it has to be smaller than the 41. In our case, this new results of deviation and noise in the gravitational wave signal will put constraints on the action field, because the order of magnitude of the squeezing will be determined from the axionic interaction with the black hole, the large occupation number, the long lifetime. For example, if we take this name parallelism of the squeezing parameter with this upper limit, we see that we can exclude long-lived action clouds through the noise that we see from the signal on the gravitational waves that we take from these axionic clouds. So, yes.
Wouldn't you get a better constraint from this recent event, the one that you've showed us that tests the aerial off? Because the signal to noise ratio is much better than the one you showed.
Yes, I think so.
So maybe people have already looked into that, or they are.
Yes, I think you have noise also in there, but the emitting gravitational waves there, it's not from the super Athens, so it means from the metal.
Yeah, like here, like the
Yeah.
one that you showed, 1509, 14, it's the same.
Yeah, I think
Except
you
that you
can
have-
get, yes.
Yeah, you just have a much higher signal to noise ratio in the new one, 25,
Yeah, probably.
40.
Yes,
And this,
with increasing accuracy.
so maybe we could get a better constraint on this R from,
But-
from
yeah.
the same type of analysis that is.
But let me mention that this also, there are other sources of noise, of course. You see. So it's a very important and challenging thing to identify this. Because you have all these sources, and how you can identify that this noise is the one word is very challenging. I don't know how to do that until for now. We hope in the future we have some science to do. So to conclude, we have this apparatus, which is a gravitational atom. It admits some characteristics that probably can enhance the EFT effects admitted to the gravitational waves. And probably it might be a good candidate in order to see this effect. But our approximation was limited. We took the flat approximation background, which is a limited one, and we see that when you go to the relativistic regime, more entanglement in bed state will be produced, which will acquire more enhancement to the exclusive parameter. The lifetime will be actually might be reduced because the dynamics are more effective and the gravitational, the coherent gravitational wave will be emitted in a more rate. So you will have probably a smaller lifetime for the cloud, but you have to see how actually this dependence gets will be occurred. Moreover, you can have more enhanced parameters because this is just a single black hole and a single gravitational atom. And at the center of the galaxy, there are a population of such black holes. So all these black holes will contribute to the noise of the signals. And this, as a collective phenomenon, will be might enhance the noise and considering the squeezed parameter. What I want to say is just I hope that this will be the starting point in order to see the superradial action cloud. Sorry. To see if we can have quantum gravity effects starting this apparatus beyond the already existing studies, which are for the beyond the Saturn study, gravitational wave signals, and this is for me. Thank you.
Thank you very much for the talk. So we had a couple of questions, but we can take a few more.
Yes.
Yes, Stefano?
No, in the for the case of photon or photonics, what plays the role of the parameter of the Chern-Simons scalar field?
Yes. You mean the Chern-Simons interaction?
Exactly, yes.
In the screen. Yeah, yes. We have had a more nonlinear dielectric, which has a polarization that is to the third order to the electric.
But so it is the form of the nonlinearity, because well in gravity one also has nonlinear interaction.
Yeah.
Are these interactions different so that one has to resort to Chern-Simons, or what happens?
You mean the difference? They are different count. But the crucial part is that you can have actually this corresponds to two photons emitting two other photons from the coherent field. This is why I make the parallels with the sorry.
It's one here.
This is the Chern-Simons, sorry. Yeah. In which you have the PAM field, the coherent field, and then you have a photon decay into the other photons. This is the Chern-Simons, which is linear to the action. Sorry. This is the general idea.
But if I may follow up on this question, so in the end, you showed that the Chern-Simons term was not so important. So
Actually, you expect that because the Chern-Simons coupling is high temperature cup. And this has more suppression than the general beer. So you might have, it could be, but it does not, at least with this analysis. It's very subdominant. It's used.
But the critical thing, if I might just, the critical thing was the linear versus quadratic dependence on population, right?
Exactly.
And this is related to the linear versus quadratic dependence on B.
Right.
If that's, so, yeah, it's not,
This is the crucial.
this is,
I was going to say that maybe in a way it's a good news. That's it's better in general relativity than in modified probability.
But it's not. Yeah, Jim?
Apologize, I missed one point was the end. Constraining parameters based on the gravitational wave gas. Oh, that was the end.
Ah, you mean on the comment? Yes,
Yeah.
yes.
So this gravitational wave gas after collision, the dynamical to the pulse, collapse. This,
I think it's merged.
this another way the mechanics we were discussing, it's a long term, there's this super alliance stability. How could you put, so we don't have the application ways to take it from that source. How could you put constraint on a certain type of process based on this gravitational wave? I could understand G like U 50 microseconds.
Yes, you cannot. This is why it's common. Actually, if these guys here are not considered the superactive.
That's why then first.
Yeah, they are different. They are just wanted to highlight that if you can have similar expressions and bounds in the gravitational waves that emit from the action cloud, this will put similar constraints on the action physics. This is just I want to highlight that this is what we have as a comment, not as
I misunderstood.
Are there any questions online? Maybe not. So since we're already a bit late, I suggest we stop here, but Panos is here for the week, so don't hesitate to talk with him again about all this, and thank you again for the talk.